Hi and welcome back. I'm Matt Turner and this is part 2 of Virtual Interfaces and Networking on Linux. This part is going to focus on some of the more advanced, newer interface types after the more run-of-the-mill ones that we saw in part 1. Some of this stuff gets quite exciting, quite complicated, so I'll do my best to explain it to you. Before we move on to that new stuff, there's one more sort of old school interface type to take care of, mostly to set this stuff in a historical context. And that's the VLAN, which you might have heard of. So the way a VLAN interface works is it uses the same physical device, as we can see here, as another interface, a sort of parent interface. It has this, so the packets have the same MAC address, but they have a different VLAN ID. This isn't an overlay network, this isn't like a VXLAN or a GRE tunnel or anything like that, if you're familiar with those. It's like a sort of side-by-side multiplex of the one interface. You can blame Cisco for it. So maybe if you think of the layer 2 address, of an Ethernet address, it's not just the MAC address, but the combination of MAC address and VLAN ID. So it takes both the MAC, which this E1000 has, and the VLAN ID to address an interface and to get you to one of those blue arrows, which is going to have an IP address. So you're meant to think of separate VLANs the same as separate physical LANs. It's a way to avoid having two separate network interfaces in your machine. So you're meant to think of these two blue arrows here as being on completely separate networks, as if one was ETH0 and one was ETH1, and they were plugged by separate wires into separate switches. So a switch, an upstream switch, not shown here, that is VLAN capable, coupled with the VLAN interface type inside the kernel, so the sort of VLAN software. It does that for you using the one physical card, the one switch, and the one cable. So this is what VLAN interfaces do. The way that happens is there's a bit of space in the Ethernet frame for this VLAN ID. It's normally 0. Those packets are called untagged. So when a sort of normal Ethernet frame hits the E1000, it gets delivered to ETH0, just like we were seeing before. If that extra field, that VLAN field, is filled in with a number, say 42, then it'll go to a different software interface. Remember, the E1000 is the hardware piece. It's one device, one driver, one PCI slot. But these blue arrows are a figment of software imagination. So what the kernel can do is extract the VLAN ID and use it to send it to any one of these virtual software interfaces on the inside. So remember, we could have just taken, we want multiple layer 3 addresses here, right? We've got two different IPs. We could have taken these multiple layer 3 addresses and put them on the same interface, like we saw right at the beginning. The kernel would respond to ARPs for each one of them. So any packet that arrived addressed for any one of them would turn up and go to the right place. The right piece of software that was bound to that IP address. But they all go out on the same LAN. Right, so if we had these two IP addresses both on ETH0, anything that was sent through either of them, with the destination address of either of them, would have the same MAC address on it and go down the same wire. And they'd be, as soon as so there'd be no isolation there, right? As soon as they left this machine, even though the reason you'd use the two addresses is to isolate the two things. Using those two different addresses, as soon as that the packets leave this machine, that context is completely lost and nothing else knows that. So this was kind of these VLAN tags were an isolation mechanism, and like I said, you rely on the upstream switch also seeing these VLAN tags and taking these things, treating these as if they're on completely separate networks, and switching everything with VLAN tag 42 from any machine, only with the other things coming in with VLAN tag 42. So that's what VLAN's for. It is, I guess, almost a historical accident that they're actually separate interfaces, right? You could have had multiple IP addresses on ETH0 and then made some, side channel configuration call to say, well, when the source IP address is the 192.168 thing, then don't tag it with the VLAN ID. When the source IP address is the 172.16, when that's the address that's being connected through or bound to, then that's the time when you're looking for or you're adding in the VLAN tag number 42. But I guess, historical, for whatever historical reason, having them actually as separate interfaces was the way that this was implemented. This is the way the kernel keeps track of the VLAN tags. So anything that goes in and out of interface eth0.42 has the VLAN tag 42, added and stripped on the way in and out. The whole mechanism is a bit historical and clunky. You sort of magic these VLAN interfaces into life you made a new interface. You sort of did an if config up of eth0.42, and that string was kind of parsed, so it would make a new sub interface on eth0 rather than eth1, and it would apply VLAN tag 42 from parsing the number, after the dot. So it was all a little bit magic. That the management wasn't very good. But it did work, and you've got these separate interfaces. You can put one or several IP addresses on them, and then they did VLAN tagging for you. So that's how that's how you could achieve sort of separate apparent networks and isolation of packets by using these different interfaces. But now the thing is, we have a stronger form of isolation, right? Previously, the upstream switch was isolating things based on these VLAN tags, but internally, every process could just see every interface. It could see eth0, eth0.42, eth0.43. So if you wanted to say you had that FTP server we see here, you wanted to keep it isolated, you had to write its configuration file. As an administrator, you had to be very careful to know which VLAN you wanted it on, know which IP address was going to be on that VLAN's interface, bind to that IP and only that IP, get that configuration right, write that config file, lock it down so nothing else could interfere with it, and just kind of cross your fingers. We now have this much stronger isolation mechanism of containers. So now if I have one of these separate interfaces, I can move it like I can move anything else into a container, into a network namespace. So this engine, there's no way this Nginx can interact with the network at all other than through VLAN 42, right? Because the only interface it can see is eth0.42. So however malicious or misconfigured it is, it can only send packets out that are tagged with VLAN ID 42. So upstream, the switch is never going to mix them with anything tagged with any other VLAN tag. So does this give us what we want for containers? It's, we've got several interfaces now. The motivation behind all of this, by the way, is to take what we saw before in part 1, but to try to remove that bridge. Because the bridge can be a bit slow and a bit clunky, and it does have some other problems. It needs management, it needs creation. So is there anything we can do to remove that bridge from the picture? Because we're saying that the right hand side of this E1000, this PCI card we want to use is all software. We now have clever software networking, sort of isolation and management techniques with the network namespaces. Can we do anything better than simulating an entire layer 2 network inside our system? So that's the kind of journey I'm going to take you on. This was the start of it historically. So we now have multiple interfaces connected to the same physical card, able to talk down the same wire, but without needing one of those bridges. The problem with the VLANs is that that isolation is too strong. It's not only isolation within our grey box here, it's isolation outside of the grey box. This if we were to have two containers in this system, they couldn't talk to each other. Which we obviously probably want them to do, and they couldn't talk to anything else on any other machine unless they lined up VLAN tags. What we want is multiple layer 3 addresses. In fact, what we want is multiple interfaces, so we can namespace them each into a different container. But we do want them all to be on the same network. The VLANs were an isolation technique, so you could effectively be running two separate networks at the same time and just save on hardware costs and on cable space. The obvious thing we can do is we can make multiple vet pairs and we can dangle each one into a container, and then we plug them all into a bridge because the bridge extends the network, and then we plug that one interface into the bridge. And we've seen that, and that does it. But it is what we're trying to avoid here, right? That bridge is slow and complicated, and I want something more direct. So if the VLANs look like this VLAN interface that the code for which sits in the kernel does look like a good idea. But in principle, it's close to what we want. It's multiple of these, blue virtual RJ45s on the inside. They're all multiplexed onto one wire on the outside, but they're actually, and there's no faked up bridges in the way, but they are too isolated. So what I don't want those VLAN tags, right? That's the thing that's isolating them. That's the thing that's forcing the upstream switch to isolate them. But that type of interface we saw before, that VLAN interface type, has to tag with the VLAN ID. That's what it's for. you think of the counterexample in the olden days when these three things were invented. Why on earth would you want more than one interface on the same network with the same MAC address? Because these things are kind of upstream. They cling to this one sort of parent interface, which is the hardware device that has a MAC address. So we've got this is the same kind of thing here. So that the Vlan interfaces, the MAC addresses aren't shown, but they all use the MAC address of the parent interface. Imagine we've kind of exploded the diagram here. We've now effectively got these three interfaces. They all have the same MAC address. We're putting them all on the same network. We're saying, why on earth would you actually ever want to do that? And if you did, why would you not just use multiple layer 3 addresses on the one interface on ETH0, right? Because everything was just visible everywhere. Well, now we have containers, and now our isolation mechanism is strong, and our isolation mechanism is taking an interface, a dangling blue arrow, and moving it into a namespace. It does make sense to want to do this. We have these three interfaces here. They all can be moved into separate containers. They can all have separate IPs. These are actually shown on different networks, but they would want to be on the same IP network, so all the containers can talk to each other, but we only want to use the one upstream wire. So this does make sense now. So to continue our thought experiment, imagine I have this. I've removed the VLAN tag because I don't want the isolation. So now, as we said, my hardware address is MAC address plus VLAN tag, but the VLAN tag is gone, and the MAC addresses are all the same because I've actually only got one physical piece of hardware. This means that really they all have the same address, right? So this is simpler than the VLAN system, and it is kind of like those multiple layer 3 addresses because we do have many of them, but each one gets their own interface. So why can't I do this? Why can't I just have the one set of MAC address, the one MAC address on my one card with its one physical wire, and then make multiple interfaces on the front that I can give IP addresses to? Well, the problem is it actually kind of doesn't work. Right, so that hardware address was MAC plus VLAN. You remove the VLAN, they all have the same hardware address. This leaves me with multiple layer 3 addresses in the same network segment. That explains why I drew the previous slide the way I did. Right, this would work because each of these interfaces is on a separate network. Well, it would mostly work. But now if I'm putting all of these addresses to be adjacent on the same network, they leave the system with the same MAC address. That's gonna. I said right at the start we can't do that. That confuses the upstream switch. It confuses the way the ARP system for address discovery works. It makes an advanced switch will have an anti-spoofing mechanism. It confuses that. It makes the switch block you from going into a thing called promiscuous mode. There's all kinds of reasons why you don't want to do this. What it turns out is I actually do want all my interfaces to have separate hardware addresses, separate MAC addresses, because there's no longer this VLAN tag to differentiate them. I actually want to vary the actual MAC, right? Otherwise, the upstream systems, the upstream switches and other systems just get very confused. But I still want that one wire. That is kind of equivalent, multiple interfaces, multiple MACs. That's several PCI cards, right? The thing is, in a modern server, I might be running hundreds, thousands of containers. I don't and can't have thousands of network cards plugged in. Even if I'm in a VM where I can magic them, I don't really want to be emulating thousands of them. And then what do you do with that 1,000 network cards for your 1,000 containers? They all have to be plugged into a switch upstream, even if it's a virtual machine with 1,000 virtual interfaces. They've got to be plugged into a virtual switch, and we're trying to reduce the load on a sort of virtual switching subsystem, right? Because it's not very fast. So the kernel has a type of interface called MAC VLAN, and that's shown here. So these aren't real NICs, as I say. They're kind of virtual child interfaces that cling to that upper one, and they use its real wire to connect to its real upstream. But they're also not like VLANs either. So they're all on the same network. They don't get tagged. The frames don't get tagged with VLAN IDs, but they do all have different MAC addresses. And as I say, this is what MAC VLAN does. Modern network cards are happy to do this, as in the driver will let you send multiple different packets out with multiple different MAC addresses. Back in the day, you actually couldn't do that. That was another one of the reasons for VLANs and whatever, was that the MAC address used by the network card was very much baked in. And it was added by the lowest levels of the hardware or firmware, and the driver couldn't alter it. Now, they say this is all a figment of software imagination, and the software can imagine this because the driver is happy to send each frame out with a different MAC address on. So you can just do this. The MAC addresses don't have to come from VETH pairs, right, and bridge ports. So this kind of system is now possible. But we've actually taken the bridge out. Remember, the whole point of this is to remove the bridge because it's slow, but we want these interfaces, these containers, to be able to talk to each other. How do they actually do that, given this system? Well, there's a few options. The first is that I can take the lower device, the sort of parent device that these Mac VLANs are based on top of, and I can put into what's called bridge mode. So this is now like having a little bridge, a little vSwitch, in the interface, actually, in that yellow box, that software side of the interface. But it has a few advantages. I don't actually have to manage it. I don't have to BRCTL it into existence. I don't have to do any of the other management things. It's a lot faster because for a start, it knows all the MAC addresses it's ever going to see, because I'm putting that parent interface into bridge mode, but it knows exactly the set of MACs that are valid and exactly what ports they're on, because they're all contained within that interface, right? We can see them all here in all those boxes that say Mac VLAN. So it doesn't have to learn them. It doesn't have to run spanning tree protocol because it knows there can't ever be any loops. But it isn't a real bridge, right? It's a very simple implementation. So there's no ports. There's none of those holes that we plug, yellow holes that we plug the blue arrows into. So I can't do IP tables filtering of the packets. I can't do rate control. I can't do anything like that. But if you don't need that, then this is sufficient, and it's much faster and it's much easier to manage. The other thing I can do, which may seem a bit weird, is I can put it into this mode. This is called Hepa Mode, or VEPA mode, Hepa Mode. And what that does is it takes the packets from the frames from each one of these Mac VLAN devices, or ETH0, the sort of parent one, and just does drop them all on the wire. It literally does it doesn't do any bridging itself. It just multiplexes them all onto the wire, like the VLAN thing did, except there aren't any VLAN tags. So upstream, they are all on the same network. And so this basically lets the upstream switch deal with it. This lets the upstream switch them. So if a frame came in through ETH0 and had a MAC address that sent it to another machine, the upstream switch would do that like it always does. In this case, actually, if the MAC address of, say, a frame goes out through ETH0 and it's got the MAC address of ETH2, then you want it to come back. And what we're doing is we're letting the upstream switch do that for us. Now, this may seem a bit silly when we can just not let it leave the host at all and bridge it ourselves like we saw before, but there are a few advantages. One, it may actually be quicker. If you've got a physically short piece of copper cable and an expensive switch, those things are super, super fast. That may well be quicker than bridging it in software at all, no matter how simple that bridge is. And also, if the switch upstream is smart, then it might be doing all kinds of clever network services for you. It might be logging every packet. It might be giving you traffic metrics. It might be doing clever filtering. It might be doing all kinds of firewall rules, all kinds of things. And that was the whole point of paying a lot of money for that device, was that there was sort of one security context per machine. Each wire that plugged into it represented one computer, which was one security context, and the filtering, any talk between security contexts went through that switch. So that's where the filtering and the auditing happened. Now we've got these multiple containers. We've kind of built a network of little pseudo machines within our system. But we may well still, if we've got all of that filtering and stuff set up in the actual physical switch, we still want to use it. So that's another example for hairpin mode. The main problem with this is the upstream switch actually has to be happy to do this, to hairpin these packets. If you think about being a switch designer back in the day, you would never, because there was only ever one MAC address and one internal software interface per sort of network card. If you've got a packet that came from one machine that was trying to go to a different MAC address, but that also seemed to be on the same machine, back down the same wire, that was always a mistake, right? Because if you remember, we said that these network cards had the one MAC address that was, the prefix of a MAC address is actually the manufacturer ID. So it was really baked in at a low level. This thing would say, I am an Intel, and I am, I was the 58th millionth Intel NIC ever made. It would make no sense for it also to be the 59th million. So that wouldn't make any sense. Now, of course, because of systems like this, it does. Your switch has to have a feature called effective relay. standardized as 8021 QBG, in case anybody was wondering, which basically is a mode you put it in, which makes it's happy to Hepa these packets back. Most switches don't do this by default because that blows SDP, spanning tree protocol, out of the water, because it is precisely a loop, which is what SDP is designed to avoid, and it'll shut ports down that look like they're going into a loop. So in this case, you have to make sure you have no loops, and you have to turn that protection off. There's one final mode called private mode, which is actually kind of getting back towards VLAN territory. This dumps all of the packets on the wire too, just like hairpin mode does. But if there is ever any hairpinning, then they get dropped on the way back in. So we say we dump a packet from a frame from E to 0 on the wire. It goes to it's addressed to E2, so it goes to the upstream switch. The upstream switch sends it back, and we say no, that's not allowed. That's not a configuration that we're ever intending. I'm not going to let that packet back in. This is here for completeness. This is kind of an odd rule to set up. So that's kind of cool for containers, right? Multiple MAC addresses. So we can actually switch packets between them. Upstream switches that can cope. Multiple interfaces that we can move into multiple containers. But what if I'm still running VMs? What if I've got a kind of old school system? What I need is not a dangling blue thing as if it's a VF end. I need a tap or a ton. So I can do this. I can get a bridge, right? I've got two mail things. How do I make them go together? I put a little RJ45 back-to-back connector in there, right? If you think of the physical analogy. So yeah, I've got a tap interface, which is mail, if you like. I've got the Mac Vlan interface, which is mail. The way to get them talking to each other, if I've got a bridge like a tap, a QEMU like you see on top of VM, is to make a bridge and plug them both into a bridge. Again, a bit slow, lots of copying around. Goes up and down as well as left to right, if you think of the diagram like that. And there's a lot to manage. So there's a shortcut. There's another interface type called a Mac V Tap, which is kind of a combination. So it's a Mac VLAN, but what's on top of it is not what it's projecting is not a blue arrow that dangles and can take an IP address. It's a tap, and what you configure is the process that it talks to, rather than the IP address it has or the bridge it's plugged into. So that's kind of a shortcut that eliminates a bridge if instead of connecting multiple containers through this mechanism, you're connecting multiple VMs. So remember, those Mac VLAN interfaces, they have multiple Macs for each interface, right? Because it really confuses upstream switches if the frames all come out with the same one. It's bad enough that there's multiple Macs that appear to be on the same machine. Your switch has to support that. But those Macs do have to be different. Well, in theory, I don't actually want that. In theory, what I want is sort of where we were here, right? But we said it wasn't going to work. Because it confuses the upstream switches. Well, actually, there's been more advances in switches. Modern switches can cope with that. And actually, if you take the Mac VLAN approach and have multiple MAC addresses, you have the multiple interfaces making multiple MAC addresses appear to come out of the same physical network card, you actually hit other problems, like the fact that switches tend to have fixed size tables for Macs. So if you've got a switch with 32 ports, and you could previously only plug 32 machines into it, 32 MAC addresses. If each one of these machines is now running 1,000 containers each, you've certainly got 32,000 MAC addresses. That's going to overflow any of these tables, because these tend to be very static, very low-level hardware tables. They are a fixed size in the firmware or something. Actually, in the ASICs in the hardware, like you're going to start overflowing those tables. So not only is this configuration we see here, where these interfaces, sub-interfaces all have the same MAC address, not only does it now work, it's encouraged. So this is yet another type of interface. This is called IP VLAN, because you don't have that MAC component of the varying MAC. Mac VLAN almost was a bit of a detour while the switches caught up, right, with what we kind of wanted, what we almost got to with VLANs. So we've got a hardware address. The MAC is the same, like it always was with that VLAN setup, but we've taken off the VLAN tag because we don't want the isolation. So we've now been left with just the one MAC as the hardware address for all of these systems. So this really is about as close as we can get to my multiple layer 3 addresses on the same interface, on the same wire. But what that adapter is adapting to is not one of those dangling blue arrows, it's multiple ones, so that we can sling them into different network namespaces and different containers can use them. And we don't mess around with layer 2 to make that happen. There is an equivalent to the Mac Tap, just to say there's a thing called Ipv Tap, which does exactly what it says on the tin. It's one of these things. But say ETH2 is now a dangling arrow. It's a tap that can be connected to a virtual machine. If you think about the way this is actually going to work on the wire, it is in some ways worse than Mac VLAN, because we've got, as I say, we've basically got those 3 IP addresses on the same interface, because all the Macs are the same. That's what it looks like to the outside world. So the bridge, the expensive switch we're paying for upstream, becomes a hub. Every packet that hits it from another machine that's asking for this one IP address, this one MAC address, this coffee MAC address here, comes down the wire and actually gets delivered to every container. And every piece of software has to wake up and decide to do nothing with it and drop it. So that's actually a disadvantage if this IP VLAN thing, it can't do that bridging, that loopback bridging that we saw Mac VLAN do. Right, because there's no way to distinguish, there's no way to tell where these packets are actually trying to go. None of these low-level subsystems understand the IPs. They rely on the Macs, and you can't do that. So it just gets broadcast. If ETH1 sends a frame aiming for coffee, then it necessarily has to be sent back to itself, to ETH0 and to ETH2. Right, and as I say, if something comes from if something wants to get to ETH1 here from another machine to 192.168.0.11, the MAC address you have to put on that frame is coffee, so it'll get delivered to all of these things. So there are some slight disadvantages to it, but maybe the advantages outweigh that. But if you take this to its logical conclusion, these Macs are all now the same. So they're kind of redundant. I've just said, there's a problem with them. A frame comes into this interface, to this physical card. It has to be delivered to all of these interfaces because these Macs are redundant. They don't help. So remember how our tap, these are virtual interfaces. They can act the way we want. So our taps have an IP address. Can have one, can have many. They also have a MAC address because they're kind of virtualized Ethernet devices. But a ton didn't. If we were only setting up a VPN, which is sort of internet thing, we don't need a MAC address, and we kind of don't want one getting in the way. So what we saw was actually IPVLAN layer 2 mode, IPVLAN L2. What we can have is a thing called IPVLAN L3, where these child interfaces, these upper interfaces as they're called, don't have MAC addresses, just like tons don't, because they don't need them. So and this is fine if and only if we're going to move these interfaces into a container, right? They can't be attached to a VM. You can't plug them into a bridge because they don't have a MAC. There's no IPVLAN L3 tap equivalent, not least because it would be quite a mouthful, right? And also because it doesn't give the VM what it needs. But we can do this. We can eliminate the MAC addresses because they were redundant anyway. There's just the one held by the lower interface, by the actual PCI card. It does its thing. It's the one that gets used for every packet that comes in and out. There are some weirdnesses to this. Like I said, IPVLAN L2 is not perfect because it has the problems with packets getting a bit broadcasty, turns switches into dumb hubs. IPVLAN L3 gets kind of even more confusing. So for a start, each IP address, you'll notice it's a bit subtle here, but these IP addresses are .1.10, .0.10, and .2.10. Each one has to be on a separate L3 segment. Because remember when I said before with IPVLAN L2, when the frame got to the main physical interface and it was in bridge mode, it couldn't bridge it. It had to hub it. It just had to send it everywhere. Now there aren't even any Macs, so this thing has to get routed. It can't be bridged. It has to get routed at the IP layer, like your home router or like a big central part of the internet does. And because you're routing, every interface has to be in a separate layer 3 network, right? A separate IP network, a separate segment, as it's called. You can't do broadcast or multicast because those are layer 2 things, so a lot of sort of network discovery services and stuff won't work. None of these things could use DHCP, right? So E0 obviously has the access to that MAC address, but nothing else could use DHCP to get an address. And they can't respond to ARPs because they don't have a that interface doesn't seem like it has a MAC address. You can't open a raw socket on it. You can't manipulate layer 2 Ethernet frames because they're just not presented to you. You only get the IP bit that would normally be the payload of one of those. You can't talk ARP or anything, so there's no way for any machines outside to find, if I make one of these new Vlan L3 sub-interfaces, stick an IP address on it, there's no way for anything to respond to the outside world. When another machine is saying, hey, I hear there's a 192.168.210 on this network, where is it? What's its MAC address? So I can actually talk to it. There's no way for this thing to reply, right? To send that ARP reply, to fill the switching tables in the switch. So even though they're directly attached to that wire, there's no bridge in the way. The kernel would happily, if it saw a packet come in with the coffee MAC address on and the 2.10 IP on, it happily deliver that packet. The packets are never going to arrive because there's no way for this machine to tell the outside world. So you have to set up static routes upstream in order to send the packets here. And worse, they're on different subnets to that native host interface to the E0. So the other machines, they need a route for each one of those subnets, right? It's not okay to say, well, 192.168. It's not one static route to say 192.168.0.* is here. It has to route these different segments. It has to route 0.*, 1.*, 2.*, all to this one place. But it is close. We have, from the inside point of view, we kind of have what we want. But there are some practical difficulties. But if only we could, if we could allocate IPs without needing DHCP, so that we didn't have to do the layer 2 thing, if we could take those routes and we could sort of dynamically install them, we could advertise the fact that we do have these IPs in a way other than ARP, so we don't have to set those routes manually on other machines, then we'd have a winner, wouldn't we? So this is what a thing called Calico does, which is an overlay network. And I say overlay network because it's got a control plane to take care of it. So there's an external agent. The way Calico works, this is just one node, one machine. There would be several. The way Calico works is to have an external controller that talks to several things. So the first thing it does is, you see there's the arrow pointing to 192.168.110. It assigns that interface, that IP address, to that interface, because DHCP can't be used. So there's a central broker for them on this control plane. It's not done on a side channel on the data plane. It's done by the central broker. The other thing it does is it talks to its own, each grey box, each machine has a special container, a management container running Bird, the Berkeley Internet Routing daemon, which is a BGP client server node. And Calico will talk to Bird, and it'll tell that instance of Bird what IP addresses it's given to all the other containers on this system. So we only show one other container, right, with 1.10. Which means that 192.168.1.* has to be routed to this machine. Then maybe there would be others with 2 and 3 and 4 and whatever. Calico knows that because it's allocated those IP addresses to them directly. Calico tells Bird, and then Bird can advertise over IP using BGP, which is an IP protocol. It can advertise to the rest of the network that these addresses are here. So that's how you get the right packets coming into the right place without using ARP. So by building that control plane on top, we can use Vlan L3. We can get what we want. We have one MAC address for actually dumping things on the wire. We have these sub interfaces. It's good that they're interfaces because they can be isolated into containers, but there are no MAC addresses on them at all. Certainly not different ones, not even the same ones. So there's a whole bunch of reasons why you do want this Vlan layer 3 setup, but it's only possible with an external agent sort of being an oracle. And just to show you how complicated it gets, you do end up in, this is Calico running on Kubernetes, so this is Calico control plane living in Kubernetes as a compute environment, but you do get all kinds of complicated things going on. So to kind of recap, Vlan layer 2 is probably what you want. If you're building a container system, you're doing you want high-ish performance, so you don't want that extra bridge. You don't want lots of big broadcast domains flying around. Then Vlan layer 3 is a step too far, really. It requires extra management. Vlan layer 2 is probably the thing for you. Docker has a network driver that uses exactly that for its containers. There's one that uses the Linux bridge. That's the default, but you can definitely switch it over to Vlan. Your physical infrastructure needs to be relatively new, or at least very configurable to cope with that. If it's not, then you can stick with Mac VLAN, which again, Docker does have a driver for. But the whole point of this series, part 1 and part 2 here, is that there are multiple interface types on a Linux system, right? Real, as I show there in quotes, your kind of classic ETH0, which is one blue arrow dangling off, the one Mac representing one PCI Express card, is only one of many types. If you think about it, and I didn't even cover it, you're already familiar with the Loopback Interface, right? Which is a virtual interface, entirely software. Only exists within that host and just loops things back, hairpins them back to anything else connected to that same interface. There's actually one called Dummy for testing. I've put multiple layer 3 addresses in brackets because your ability to give one interface multiple IPs, perhaps on separate IP networks, in separate segments with a different prefix, is quite a powerful thing that can be used. We saw tap and ton. We saw veth pairs. We saw the older Vlan interfaces. We saw Mac VLAN and its Mac V Tap shortcut equivalent. We saw Ipv VLAN at layer 2, and we saw Ipv VLAN and Ipv Tap at layer 3. Also, bridges, where for the types of interface that exist at layer 2, we are plugging into bridges. There's the built-in Linux bridge implementation. There's Open vSwitch. There's the DPDK optimized Open vSwitch, which basically is Open vSwitch that can do meaningful work across multiple cores. There's Mac V Tap, which is basically a type of bridge, right? And then there's the faster stuff that are custom implementations that run a lot of their own code in the kernel and carve through the Linux networking stack. So there's the snap switch, there's netmap veil, and then there's things like SRIOV network interface cards, which are, they're basically multiple interface card, multiple network interface, so multiple of the hardware E1000 side of things, and the switch in one PCI card, so they only take up one slot. So where, I said you can't have 1,000 cards in a machine to deal with 1,000 containers, but you can get a lot closer if you've got 8 PCI slots, and each one has sort of 16, looks like it has 16 interfaces on it. You can get a lot closer to 1,000 than you could if they only had one interface on them each. So I hope that was useful. Thank you for your time. This QR code links you to a page that's kind of got this recording on. It's a self-link and it's got some more resources. I'm on Twitter if you want more nerdy videos like this. Thank you very much for your time.